All right, ladies and gentlemen, this class recording has started. So, yesterday, to introduce the idea of voltage, we talked a lot about gravitational potential energy. And then we discussed how gravitational potential energy was similar in many ways to electric potential energy. So, what I would like you to do is take 1 minute, discuss with the person next to you, how are gravitational potential energy and electric potential energy similar to one another? Discuss. Go. Well, let's go similarities first, because that's I wanted to look at similarities. Alright, let's discuss. So, what makes electric potential energy and gravitational potential energy similar? Right, good. They are both forms of mechanical energy. Good. What else? There's one kind of more important thing we should go there. Okay. They both have to deal with what? Position. And more specifically, they both have to deal with position where? Within a field, right? Gravitational potential energy deals with position within a, fill in the blank. Now, gravitational potential energy deals with position in a gravitational field, and electric potential energy deals with position within an electric field, right? So, we said that in order to increase the electrical potential energy, we could do one of three things. What can we do to increase electrical potential energy? What's one way? Dylan, go ahead. Move positives closer to positives. That was good. Move negatives closer to negatives. Or Jafar, go ahead. Move positives away from negatives. In any of those three cases, we are doing what to a charge? We are doing work on a charge. And more specifically, we are doing work against the electric field. All right, that's important. We'll use that idea a little bit later on. So, we can increase electrical potential energy by moving positives closer to positives, negatives closer to negatives, or positives away from negatives. In any way, in any of those three situations, they don't like where they are. They're trying to get somewhere else, right? That increases energy, but it only happens if we do work, right? So, a couple other ways that we can increase the potential energy. One, up here on the board, you have two pictures, there's two pictures, and you have these two pictures as well, okay? If this charge here, that I have the yellow circle with the plus sign in it, if it moves from left or from right to left in both cases, one on the left, one on the right, which one do you think it's going to gain more potential energy?
The left.
One on the left, right? Why?
Because it's strong.
Strong field, right? If we do more work, or if we work against a stronger field versus a weaker field, we're going to gain more energy. Just like if we took this ball and raised it to a height of, 2 meters, right? Here on Earth versus on the moon, would it be able to do the same amount of damage on the moon as it does on Earth? There's less gravity on the moon, right? There's a weaker gravitational field. Here, right? So if you go back to your outline, letter F, two ways that electrical potential energy can increase other than changing the position. One thing we can do is change the what? Change the strength of the electric field, right? We can change the strength of the electric field. That will change the electrical potential energy. And then, right, it also depends on the size of this charge that we're moving around, right? A bigger charge, if you move it against an electric field, will have more potential energy than a smaller charge. Just like if I have a larger mass of an object, it'll have more gravitational potential energy. Does that make sense? Yeah. So, change the strength of the field or change the size of the charge. Either one of those ways, we can increase the electric potential energy without changing the position. Okay? Jules, go ahead. All right, so what's E? All right? So, in order for us to increase the energy, we have to do work. But we have to do work how? Somebody said Jules can answer this question too. How do we have to do work? We have to move a charge. True. How do we have to move it, though, in the field? Start using the proper terminology. So, if I move this charge, which way is it going to increase the energy? In either one of these pictures, how do I have to move the charge to increase its energy? From right to left, or towards the positive. That is against the electric field. So against the electric field increases the energy. But, I'll do this. Right? So if we move it this way, right, that's against the field, that increases the energy. It won't stay there though. If we let it go, this will happen. Right? What about if we move it this way?
It stays the same.
Nothing changes there, right? It doesn't have any more or less energy. So how can we move a charge that it doesn't increase its energy?
We move it vertically.
Let's start using some math terms. Because vertically and horizontally change if I change this board from one way and tilt it a different way, right? How do we move it in relation to the electric field? Parallel. If we move it parallel, that would be moving it left or right on the board, right? But that changes the energy. If we move it perpendicular to the electric field, we haven't moved it any closer or farther from the other positives. Just like if I take this ball and I hold it this high off the ground, but then I switch it from my right hand to my left hand, as long as it's the same height off the ground, does it have any more potential energy? Right? Perpendicular is at a 90-degree angle, right? That sound familiar from math class? Okay. So in this case, in the case of this picture on this board, perpendicular would be up and down because the field arrows run left to right. Right? Say again? Yeah. That's why I pointed at him and went, ah. No. So Jules, to answer that question, right, how can a positive charge move in the field without changing its potential energy? How do we have to move it? Perpendicular to the field. Okay. All right, good there. We good? Yeah. Okay. All right, so go here and here. All right. All of this, go ahead, Jafar. Yep, change the strength of the electric field, or, so for letter F, right, you can either change the strength of the electric field or the size of the charge. All right, all this discussion about electric potential energy is very synonymous with gravitational potential energy, but we said that the first unit that we do in this class is about energy. And why? What's our definition of energy? The ability to do stuff. The ability to make things happen. Right? The ability to do damage. All of our electrical components that we use in our society, and our society is full of them, right? The end goal is to do stuff, right? You want to light up the room, or you want to make your room warmer, or, you know, you want to, I don't know, play some game or whatever you do on your phone or whatever it is, right? So the ability to do stuff, that energy aspect is important. So measuring that energy aspect is also important. And we accomplish that through what we call potential difference or voltage. So the potential difference tells the ability of an electric field to change the electric potential energy of a positively charged particle. That's like the by-the-book definition. But for our purposes, we're going to talk about voltage in terms of the difference in electrical potential energy of charged particles at different places in the electric field. So these three terms, voltage, current, resistance, we're going to talk a lot about them over the next couple of days. Whenever we talk about voltage, voltage always relates to energy. So when we talk about the voltage of a source or the voltage of a battery or something like that, that always comes back to energy. So voltage equates with energy. Keep that in mind as we move our discussion forward. Okay? Voltage relates to energy. And as a result, when we are measuring voltage, we have to take energy into consideration. Good? So, we measure voltage in a unit called the volt. But if you look at how the volt is defined, volt is a derived unit, so it's a combination of units. It's joules over coulombs. What did we say joules is the unit for? Joules is the unit for energy. And coulomb is the unit for what? Charge. So voltage measures energy per charge, or how much energy does each charge gain in this situation. Right? So voltage relates to energy, and we measure it as such. How much energy do those charges gain in a specific situation? Richard, go ahead. Yes, it's basically talking about how much energy will a charge gain if we move it in this electric field. Okay? That's what voltage takes into account. But Rachel, more for our understanding purposes, as long as you realize that whenever we discuss voltage, we're talking about energy, that will help you understand things. Okay? But yeah, specifically it's talking about energy per charge, but as long as you understand that voltage and energy are talking about the same thing, we'll be good. Okay? Alright, so let's take a look at this picture. You guys have this picture on the second page of your outline. And if you thought yesterday's animation with the ball going up and then coming back down was awesome, just wait till you see this. Because, whoa, I mean. Alright, so before we talk about that though, before we see some sweet animation, we have to talk about what this first is. So this is an electric circuit, alright? Just like the electric circuits, well not just like, but similar to the circuits that exist in your house or in your phone or in any other electrical component that we use. These electrical components allow us or are meant for us to do stuff. So they have to have energy, right? Or at least a source of energy. And that energy is a battery. Now, this battery is labeled as source of electricity, but I don't like that because electricity is too general. So where it says electricity, cross out electricity and write source of voltage. And Rachel, that means that it's going to be basically our source of what? Energy per charge. Okay? Now, something that's on my drawing up on the board that isn't on your drawing are these arrows, right? What do we say the arrows represent? Electric field, right? And if you look at how those arrows are drawn in that battery, which way do they point? Towards the negative, right? Positive to negative, because that's how field lines are drawn. Now, if we talk about charges, what we'll see here, okay, let's do this. Okay. So, something has to carry that energy, and those charges carry the energy. But usually it's a lot easier for electrons to move than it is for protons, right? Protons are stuck in the nucleus, electrons are on the outside, much easier for them to move. So, the first thing that happens, electrons move within the field inside the battery in order to gain electrical potential energy. Inside of a battery, there is a chemical reaction, and that chemical reaction creates an electric field. How do we have to move electrons to make them gain energy? You can either talk about it in terms of the sides of the battery or the direction on this picture specifically. How would we move electrons for them to gain energy? How can we cause things? There are three ways that things can gain energy. How can we cause things to gain electrical potential energy? You said one of them right before. Kat, what's one? Positives closer to positives, or negatives closer to negatives, or positives and negatives farther away. So, we're dealing with electrons here. Electrons have what charge?
Oh, negative.
Negative, thank you. Thanks. We've only talked about that for the last like 6 weeks, right? So electrons have a negative charge. So how do we have to move them in this battery to make them gain energy? Towards the negative, right? So, are you ready?
Yeah. Well, I'm not ready.
Whoa.
What? I looked away. Whoa.
Right, so the electrons move through the battery, and as they move through the battery, they gain energy, electrical potential energy. Batteries are not sources of electrons, they are sources of energy. What electrons are we dealing with here? Well, they're all negative, but where do the electrons come from? They come from the battery, or they come from this wire, or they come from this light bulb. Circuits use the electrons that are already there. The battery increases the energy of the electrons that are already there. Okay? Now, we've moved this electron in a way that it has gained electric potential energy. But what happens to things that gain electric potential energy? They want to lose that electric potential energy. So they will move themselves in a way to get rid of that electric potential energy. When this ball gains gravitational potential energy, how does it lose that gravitational potential energy? It falls, and as it falls, it gains kinetic. Same thing happens here. Something that is gaining kinetic energy is going to have to start doing what?
Lose that potential.
How do things gain kinetic energy? They start to move, right? So, all right, don't blink. Ready? Here we go. As electrons move within this wire, electrical potential energy is turned into kinetic energy. And now we have those charges moving. You realize this is being recorded, right? Okay. All right. So, Electrical potential energy can be turned into kinetic, but it can also be turned into a couple other forms of energy, right? Ready? You guys have this written down? All right, here's the next one. Here we go. Ready?
Oh my goodness.
Okay. As those charges move through the different components of the circuit, some of those components will take electrical potential energy and turn it into other things like light or heat. What are some other things that electrical potential energy might be turned into?
Sound energy.
Sound, if you have like a speaker that works on a battery, right? What else?
Light energy.
Light bulbs light bulbs do light and heat, right? If you guys have an electric heater, you know, somewhere in your house, or a little like space heater or a toaster, right? Okay. Okay. Anybody ever have like a remote control car or a remote control airplane or something like that? That turns electrical potential energy into what? Movement, kinetic energy, but it's not the kinetic energy of the particles, it's the kinetic energy of, oh, hold on. Still have like 3 minutes left. Chill out. Alright, but eventually the electrons get back to the other side of the battery. Now they're at the positive side of the battery. How much potential energy will they have here? None. If positives and negatives are close together, that's no potential energy. They like that situation. So one of the key components in analyzing, or kind of the key ideas in analyzing a circuit is, as those electrons move through the circuit, any potential energy that they gain from the battery has to be turned into other forms of energy as it moves through the circuit. Okay? Alright, everybody. Have a good break, and I will see you guys on Monday.